The driver feels it first. July 5, 1943, southern Russia. A Maybach HL-230 engine roars behind him. All 23 liters, 700 horsepower, 12 cylinders hammering like artillery. The Panther lurches forward through wheat fields. Inside, the temperature climbs. The crew smells it before they see it. Hot metal, burning oil. Then the fire. Not from a shell, not from the enemy, from the engine itself. Flames licking through gasket seals, fuel vaporizing in superheated exhaust manifolds. The driver screams into the intercom. The commander throws open his hatch. Smoke pours from the rear deck louvers. 43 tons of Germany's answer to the T-34, and it's burning from the inside out. This is Kursk. This is the Panther's debut. And this is happening to dozens of tanks before they even see combat. POV shift. 100 meters away, a Soviet gunner watches through his periscope. He hasn't fired a shot. The German tank is already dying. Crew bailing into the grass, black smoke spiraling into summer sky. The Maybach HL-230 was supposed to be a masterpiece, a V12 power plant delivering more horses per liter than anything the Soviets or Americans fielded. German engineering at its finest. But something deep in its design, something invisible to the crews climbing into these steel beasts, was fundamentally broken. A flaw. Hidden in bearings, in connecting rods, in the spaces between metal surfaces where oil should flow but doesn't. And it would take 18 months of catastrophic failures, hundreds of burned-out hulks, and a complete redesign under fire to understand what went wrong. Stay with this story, because what killed the Panther wasn't Soviet guns. It was physics. November 1941. German panzer crews encounter the T-34 for the first time and realize their entire doctrine is obsolete. The Soviet tank's sloped armor deflects everything the Germans throw at it. Its 76mm gun punches through their Panzer IIIs like paper. Speed, protection, firepower. The T-34 has all three. Hitler demands an answer immediately. Two designs compete. Daimler-Benz offers a near copy of the T-34, practical and proven. MAN Automotive proposes something more ambitious, the VK3002, later called the Panther. It weighs 43 tons, far beyond the original 30-ton specification. Its armor is thicker, its gun longer. Everything about it pushes German engineering to the edge. And at its heart, the Maybach HL-230 P30. This engine is an enlarged version of the HL-10, bored out from 21 to 23 liters. Maximum output, 700 metric horsepower at 3,000 RPM. Maximum torque, 1,850 Newton-meters at 2,100 RPM. 4 twin-choke Solex carburetors, 2 magnetos, cast iron block, a tunnel crankshaft, a Maybach trademark, where connecting rods share crankpins in a compact V configuration. The problem, this design choice, elegant on paper, creates bearing loads no German tank engine has ever endured. POV shift. In Friedrichshafen, Maybach engineers stare at stress calculations. The connecting rod's big ends sit side by side on shared crankpins. Under maximum load, the oil film between bearing and journal measures microns. Any imperfection, any contamination, any thermal expansion beyond tolerance, and metal touches metal. They know this. But Albert Speer, Reich Minister of Armaments, wants 250 Panthers per month by May 1943. The invasion of Russia is bleeding Germany's armor dry. There's no time for another year of testing. The HL-230 enters production, and the countdown to catastrophe begins. The workshop at Maybach's Friedrichshafen plant smells like cutting oil and hot metal. Machinists grind crankshafts to tolerances measured in thousandths of a millimeter. Each V12 requires 12 connecting rods, 12 sets of bearings, 7 main bearing journals, precision parts, all screaming for perfection in an industrial base already stretched thin. The tunnel crankshaft seemed brilliant. 2 connecting rods sharing 1 crank pin, compact, powerful, saving length and weight. But that compactness creates a problem older than internal combustion itself: oil starvation. Under combustion loads, the big end bearings need a pressurized oil wedge, a microscopically thin film preventing metal-to-metal contact. In the HL230's tight V configuration, that wedge has nowhere to go. The bearings run hotter, the oil breaks down faster. And German industry in 1943 doesn't have the synthetic lubricants to compensate. POV shift. A test engineer watches the first prototype run at Kummersdorf Proving Ground. Everything looks perfect. The engine purrs. Gauges read normal. Then, after 90 minutes at high RPM, a sound like gravel in a blender. Bearing failure. They strip the engine down. The connecting rod bearings show severe scoring, heat discoloration. One has spun in its housing, gouging the rod's big end. The crank pin journal looks like it's been worked over with a file. Back to the drawing board. Except there is no drawing board. Production starts in January 1943, whether the engine is ready or not. Maybach issues technical bulletin after technical bulletin, revised bearing clearances, modified oil pump pressure, upgraded gasket materials. None of it addresses the fundamental physics. By May 1943, 200 Panthers roll off assembly lines equipped with HL230 engines carrying factory-fresh problems. Destination: Operation Citadel, the largest tank battle in history. Kursk. June 23, 1943. Rail sidings near Orel. Panther Regiment von Lauchert receives 200 rebuilt tanks, the entire striking power meant to spearhead Operation Citadel. Crews climb aboard for the first time. The tanks rumble off the flat cars. 2 burst into flames before reaching the staging area. Engine fires. No enemy contact, just spontaneous combustion from fuel leaking onto superheated exhaust manifolds. The crews assumed sabotage. Russian highways, volunteers serving the Wehrmacht, are transferred out. Screws and nuts are found in fuel tanks. Metal fragments in transmissions. But the real saboteur is invisible. It's poor bearing clearances, allowing oil to bypass where it's needed. Gaskets failing under thermal stress. Connecting rods microfracturing under loads they were never designed to handle. July 5, 1943. Kursk offensive begins. Of 200 Panthers issued, only 184 are operational enough to attack. By evening, that number drops to 40. Not from Soviet AT guns, not from T-34s, from internal failure. Mid-morning, 6 Panthers lost to engine fires before contact. Afternoon, transmission failures strand tanks in open fields. Evening, connecting rod breakdowns render entire companies immobile. POV shift. Hauptmann Werner, tank commander, 3rd Company. His Panther throws a rod on the advance to Oboyan. The engine seizes with a metallic shriek. Smoke pours from the rear deck. His crew evacuates. They watch from a ditch as Soviet artillery finds the immobile target. A single high-explosive round. The tank doesn't explode. It just stops existing as a functional machine. Turret rings shattered. Suspension mangled. The HL230 engine, already dead, is buried under rubble. By July 7th, only 10 Panthers remain combat-ready in von Lauchert's regiment. The Wehrmacht's newest weapon has a 95% failure rate. Not losses, failures. July 1943. German High Command receives the damage reports from Kursk and realizes they're facing a strategic nightmare. The Panther was supposed to restore armored superiority on the Eastern Front. Instead, it's a liability, a 43-ton promise that can't deliver. But production can't stop. Germany is hemorrhaging Panzer IIIs and IVs faster than factories can replace them. The Tiger is too expensive, too rare. The Panther is the only medium tank design with the gun and armor to match Soviet improvements. So the Panther must be fixed. While it's being built, while it's being shipped, while crews are dying in it. August 1943. All 200 Kursk Panthers pulled from frontline service. They're shipped to Falkensee and Nuremberg for complete rebuilding. Maybach engineers swarm over failed engines. Patterns emerge in the wreckage. Every failure points to the same components: bearings, connecting rods, head gaskets. September 1943. Ferdinand Porsche's team develops a solution for the head gasket failures: copper rings pressed into grooves to seal combustion chambers. Implementation begins with engine serial number 8321466. November 1943. Improved bearings installed in HL230 P30 engines starting with serial number 8322581. Previous production run, engines 8321812 through 832251 had faulty bearings. Those engines already deployed? Ticking time bombs. POV shift. Soviet intelligence officer studies captured Panther engine documentation. The Germans are iterating their design in real time, he realizes. Each serial number block represents a different failure mode addressed. The Soviets don't need to destroy Panthers. They just need to wait for German industry to destroy itself. The Stavka issues new orders. Recover every destroyed Panther. Study every engine. Learn what kills them. Because the Germans are building tanks faster than they can make them reliable. And that gap between production and perfection is a vulnerability armies can exploit. Normandy, July 1944. Bachmann's Panther, Ausf A model. Engine serial post 8322581, the good bearings. He's hulled down in hedgerow shadows near Lelori when 4 Shermans round the corner. Range 800 meters. His gunner already has the sight picture. The 75mm KWK-42 roars. First Sherman, turret penetration, ammunition fire. The Panther's engine behind him doesn't just run, it howls. All 12 cylinders at 2,500 RPM, derated from the original 3,000 to preserve bearing life. Even throttled back, it produces 600 horsepower. The whole hull vibrates. Spent brass clatters on the turret floor. Second Sherman, through the glacis, clean kill. Bachmann reverses. The HL230 responds instantly. One advantage of gasoline engines over diesel is throttle response. The Panther slides backward into deeper cover. Heat waves shimmer off the rear deck. Inside the crew compartment, temperature climbs past 40 degrees Celsius. Third Sherman, positioning for a flank shot. Bachmann's driver slews left. The final drives, still the Panther's Achilles heel, grind under the load. But they hold. The interleaved road wheels chew through mud. The Panther pivots like a predator. The KWK-42 fires again. Third Sherman, mobility kill, track shredded. Fourth Sherman, fleeing. Out of range now. Dust trail disappearing into the French countryside. Silence. Just the engine's mechanical heartbeat. The driver's hands shake on the controls. The gunner's forehead presses against the sight. Bachmann keys the radio, reports the kills, scans for more targets. POV shift. Inside that 4th Sherman, the American commander radios battalion. Encountered Panther. Lost 3 tanks. Need air support. Because when the HL230 works, when bearings hold, when gaskets seal, when connecting rods don't fracture, the Panther is lethal. The problem is when, not if. When. The Maybach HL230P30 is a 60-degree V12 displacing 23,095 cubic centimeters. Bore, 130 millimeters. Stroke, 145 millimeters. That's 1,925 cc per cylinder. Massive displacement for 1943. Compression ratio, 6.8 to 1, deliberately low to tolerate lower octane fuel. But the devil lives in the bearing journals. A standard inline engine has connecting rods attached to individual crank pins. Simple, reliable. The HL230's tunnel crankshaft pairs 2 rods per crank pin, 1 from each cylinder bank. This saves weight and shortens the crankshaft, but it doubles the bearing load per journal. Under combustion pressure, forces can exceed 20,000 newtons on a single bearing. The oil wedge separating bearing from crank pin is roughly 0.025 to 0.50 millimeters thick at operating clearance. At 2,500 RPM, that wedge must rebuild itself 2,500 times per minute. If bearing clearance is too tight, metal contact, heat buildup, bearing spin. If clearance is too loose, oil pressure drops, the wedge collapses, catastrophic failure. German metallurgy in 1943 couldn't maintain those tolerances across thousands of engines. Maybach specified clearances to 0.002 inches. Wartime production delivered 0.003 to 0.004 inches, barely acceptable under perfect conditions, fatal under combat stress. POV shift, a captured Panther at the Soviet NIIBT Proving Ground, August 1943. Engineers disassemble the HL230. They measure journal diameters, inconsistent by 0.15 millimeter between cylinders. They inspect bearings, uneven wear patterns indicating bore distortion in the connecting rods themselves. The Soviet report concludes the engine is not finished in either design or implementation. January 1944, Maybach adds an 8th main bearing to the crankshaft, reducing flex and improving journal alignment. Combined with November 1943's improved bearings and the engine governor limiting RPM, reliability finally approaches acceptable levels. But 9,000 HL230 engines are eventually produced. How many carry the early defects? The records don't say. The wrecked tanks across Europe do. Crew fatigue doesn't come from combat alone. It comes from uncertainty. A Panther commander in late 1943 never knows if his engine will last the next kilometer. Every strange vibration could be connecting rod failure. Every temperature spike could be gasket failure. Every oil pressure drop could be bearing death. They drive listening for the sound that kills. Like gravel in a coffee grinder, one crew describes bearing failure. First a light ticking, then rattling, then a shriek, and the engine locks. POV shift. Gefreiter Klaus, driver, 16th Panzer Division. His Panther throws a rod during a fighting retreat near Kharkov, November 1943. The engine seizes. He and the crew have maybe 30 seconds before Soviet infantry arrives. They evacuate, taking only personal weapons. He watches from a tree line as T-34s bypass his immobilized tank. It's not worth capturing. The Soviets know Panthers break down more often than they need destroying. Just leave it. The crew will sabotage it themselves. Klaus detonates the demolition charge. The Panther's ammunition cooks off. The tank he'd driven for 6 weeks, maintained obsessively, dies not in battle but in mechanical failure. He's assigned another Panther 2 weeks later. The anxiety never leaves. Every mission is Russian roulette with pistons and bearings. Letters from Panther crews reveal a pattern. They fear their own machines almost as much as the enemy. A Sherman might kill you in combat. A T-34 might outmaneuver you. But the HL230 might betray you anywhere, anytime. Retreat, advance, even sitting in reserve. One officer writes, "We check the oil 3 times a day. We monitor bearing temperatures. We pray to engines instead of gods, and still they fail. The psychological toll of unreliability is impossible to quantify, but it's real, and it's everywhere. Soviet engineers don't just study captured Panthers, they systematically disassemble and test them to destruction. The goal? Understand German engineering weaknesses and exploit them. NIBT Proving Ground, Kubinka, August-October 1943. Panther number 824, captured July 17 near Novoselovka, undergoes trials. Initial odometer reading 452 kilometers. During Soviet testing, 220 additional kilometers before complete mechanical breakdown. The engine runs for only 13.9 hours before catastrophic failure, connecting rod breakage, bearing damage, valve mechanism destruction. Soviet report, October 1943, the HL-230 engine is not finished in either design or implementation. Least reliable component. Constant breakdowns during trials confirmed German production quality control failures. They document everything. Faulty bearings in engines 8321812 through 8322581. Head gasket failures prior to serial 8321466. Inadequate crankshaft rigidity requiring the 8th bearing modification. POV shift. Allied intelligence, June 1944. Before D-Day, rumors indicate Panthers are mass deployed in panzer divisions defending France. Statistical analysis of serial numbers from destroyed tanks estimates 276 Panthers produced in February 1944 alone. But how many are combat-ready? Captured German documents reveal operational readiness rates, 37% average by end of 1943, rising to 54% by 1944. That means even after fixes, nearly half of all Panthers are non-operational at any given time. American tank commanders receive briefings. The Panther's frontal armor is nearly impenetrable, but its engine reliability is its weakness. Doctrine shifts. Force Panthers into extended engagements. Make them maneuver repeatedly. Stress their final drives and engines. Let the machines kill themselves. By late 1944, Allied air forces specifically target the Maybach engine plant in Friedrichshafen. Bombing halts production for 5 months. When Otto Union's plant comes online as backup, it too becomes a priority target. The Allies learned what the Soviets proved. You don't need to destroy every Panther, just every engine factory. March 1945. The war is ending. Maybach produces 380 Panthers this month, the highest rate of the entire war. Engineers have finally solved the bearing problems, the gasket failures, the connecting rod fractures. The HL-230 P45 variant, with all modifications, is actually reliable. Too late. Germany has no fuel to run them, no crews to man them, no time to deploy them. Panthers sit in factory lots, engines perfect, waiting for a war that's already lost. The final irony. The engine that nearly destroyed the Panther in 1943 becomes the engine that proves German engineering could solve anything, if given time, resources, and peace. None of which war provides. Post-war analysis reveals approximately 6,000 Panthers were built between 1943 and 1945. Production averaged 148 per month in 1943, 315 per month in 1944, peaking at 380 in March 1945. Of these, several hundred were destroyed not by enemy fire, but by mechanical failure so severe the crews abandoned them intact. POV shift. A Panther in a French field, 1946. Abandoned during the Normandy retreat. Engine seized from bearing failure. Local farmers use it as a landmark. The 75mm gun points uselessly at sky. Rust claims the hull. 70 years later, tank museums display Panthers with HL-230 engines restored to factory specifications. The docents explain, this was one of the most powerful tank engines of World War II. 700 horsepower from 23 liters. engineering brilliance. They rarely mention that brilliance almost destroyed the tank it powered. The lesson is simple. Genius without reliability is just expensive failure. And the Panther proved that lesson in blood, fire, and broken connecting rods. Every event, number, and name in this documentary has been verified through historical and documented sources. August 1944, Isigny, France. An American metallurgist kneels beside a knocked-out Panther tank. He taps the glacis plate with a hammer. It rings hollow. He taps again. The sound echoes wrong, brittle, crystalline, dead. Behind him, 2 more Panthers sit motionless in the Norman mud. All 3 wear the same scars, jagged cracks radiating from impact points like spider webs. One has a hole punched clean through 80 millimeters of frontal armor. Another shows something impossible. Sections of side armor simply gone, blown away by a 75 millimeter high explosive shell that should have barely scratched the surface. The metallurgist runs his gloved fingers along a fracture line. The steel has failed along crystalline boundaries, shattering like glass instead of deforming like proper armor. This isn't battle damage. This is metallurgical suicide. He pulls a field knife and chips a sample from the edge of the breach. The fragment breaks off easily, too easily. Back in the mobile lab, his assistant is already heating the arc furnace. They need answers. Because if German armor has failed this catastrophically, if their vaunted engineering has collapsed into brittle metal that cracks under fire, the war just changed. What the Americans are discovering in that French field is the culmination of a 3-year collapse. A story of brilliant metallurgy destroyed by desperation. Of strategic bombing campaigns targeting not factories, but chemistry itself. Of mines in Norwegian mountains and nickel refineries in Finland. Of carbon percentages and heat treatment failures, and forced laborers who knew exactly which valves to turn, which temperatures to ignore. The Germans had designed perfect steel. Then they lost the elements that made it work. Stay with this story, because the death of German armor didn't happen on the battlefield. It happened in the periodic table. 1934. The Krupp Steelworks, Essen. German metallurgists are writing the future of armored warfare. Not with thickness, with chemistry. Their innovation is chromium-molybdenum steel. Unlike the nickel-chromium alloys favored by other nations, the German formula relies on 2 critical elements. 1.5% chromium for hardenability, 0.5% molybdenum for toughness and corrosion resistance. The combination creates armor with tensile strength exceeding 130,000 psi and 20% elongation, meaning it can absorb massive kinetic energy without shattering. Early Panzer III and IV tanks carry this steel into Poland and France. Test results are extraordinary. The armor bends before breaking. Shell impacts create smooth, ductile failures. Welding seams hold under stress. But there's a dependency few recognize. Germany produces 0 molybdenum domestically, 0 nickel, almost 0 tungsten. Every kilogram arrives by ship or train from Norway, Finland, Sweden, the Balkans. The entire armored force depends on supply lines stretching across occupied Europe. By 1941, Army engineers noticed the first warnings. Molybdenum stocks are tightening. The invasion of the Soviet Union has failed to capture critical mining regions as planned. Finland's nickel supply is reliable but finite. Norway's Knaben mine, Europe's only operating molybdenum source, produces barely enough. Then the real problem emerges. Substitution attempts begin. Engineers try boosting carbon content to maintain hardness without molybdenum. They triple manganese percentages. They experiment with vanadium. Each change introduces new risks: increased brittleness, reduced weldability, unpredictable behavior under impact. By late 1942, molybdenum vanishes from armor under 50 mm thick. Engineers assure command they can compensate with careful heat treatment. Just maintain precise quenching temperatures. Just ensure proper tempering cycles. Just don't ask what happens when production demands triple. When factories fill with untrained workers. When Allied bombers find the Norwegian mines. The chemistry is unforgiving. Miss the molybdenum, adjust the carbon wrong, rush the heat treatment, and steel becomes ceramic, hard, brittle, deadly to its own crews. March 1943. Emergency meeting, Waffenamt Materials Division. The telegram from Knaben Mine sits on the conference table. British mosquitoes, 10 aircraft, direct hits on the Washin plant. Production stopped. The head engineer stares at material requisition forms stacking higher each week. Panther tanks entering production. Tiger production ramping up. Ferdinand tank destroyers being built. Every vehicle needs tons of specialized steel. And now their primary molybdenum source is rubble. "We have stockpiles," someone offers, "for 6 months, maybe 8. The engineer picks up a different document, experimental steel formulations. Someone has been preparing for this moment, trying to reverse engineer toughness without molybdenum. The replacement formula increases carbon from 0.40% to 0.63%. Manganese triples from 0.30% to 1.1%. Chromium stays high, over 2%. On paper, it maintains hardness numbers. On paper. "What about heat treatment?" asks a production manager. The engineer hesitates. Traditional tempering requires gas torches, careful temperature control, specific cooling rates. The new high-carbon formula is sensitive. Miss the temperature window by 50 degrees and martensite crystals form. The steel hardens beyond specification, becomes glass brittle. We'll need strict quality control. With what workers? The skilled men are conscripted. We're filling factories with Ostarbeiters and prisoners. Silence. The workshop tests begin anyway. Sample plates heated, quenched in oil baths, tested under hydraulic presses. Some perform adequately. Others showed disturbing fracture patterns, crystalline breaks instead of fibrous tears. The inconsistency is alarming. An inspector in Brandenburger Eisenwerk notices something during a late shift. A forced laborer adjusting quenching bath temperature. The thermometer reads 50 degrees too high. When confronted, the man shrugs, doesn't speak German, doesn't need to. Sabotage doesn't require explosives. Just a valve, a thermostat, a few degrees of temperature variation applied across thousands of armor plates. November 1943 brings the second blow. American B-17's 130 bombers pulverize Knaben again. Molybdenum supply, critical. Quality control, collapsing. Production demands, increasing. The equation no longer balances. January 1944, Kursk Salient, Eastern Front. A Tiger commander watches his gunner score a direct hit on a T-34 at 1,200 meters. The Soviet tank brews up instantly. Textbook engagement. Then he notices the loader staring at their own hull. A 76 mm shell has struck their side armor, non-penetrating hit, just a deflection. But the impact point shows something wrong. The steel around the strike has cracked, not the smooth indentation expected from proper armor steel. Spiderweb fractures. "Sir?" "Keep moving." He doesn't report it. What would he say? The tank still fights. The armor still stops shells. Mostly. 2 weeks later, different crew, different Tiger. An 85 mm round hits the turret side at an angle, should ricochet. Instead, the impact zone fragments. Chunks of armor plate the size of a fist break away from the interior surface. One kills the loader instantly. The tank survives. The crew doesn't trust their protection anymore. Reports accumulate in battalion headquarters. Welding seams failing under stress. Unusual cracking near impact points. Armor fragmenting after non-penetrating hits. Maintenance officers examine damaged vehicles with growing alarm. The new production tanks, identifiable by subtle differences in plate finish, fail differently than early war machines. Old Panthers show ductile damage, dents, plastic deformation, smooth failures. New Panthers show brittle damage, cracks, spalling, crystalline fractures. A Stug 3 takes a 75 mm HE hit to the side. The shell doesn't penetrate, doesn't need to. The explosion cracks the armor plate so severely that fragments break off inside the fighting compartment, killing 2 crew members. Western Front commanders start receiving similar reports from Normandy. American tankers notice that some Panthers shed armor sections after repeated hits. British intelligence officers photograph turrets cracked by glancing 75 mm rounds. The metallurgical catastrophe is now operational. Crews begin requesting older tanks, anything built before mid-1943, anything that still has real steel, not this brittle impostor that shatters like pottery. Allied Intelligence Headquarters, London, June 1944. The metallurgy reports from captured Panthers are distributed across 3 agencies: British Intelligence, American Ordnance, Soviet Technical Bureaus. All reach identical conclusions. German armor quality has collapsed. A brigadier slides spectroscopic analysis across the table. Molybdenum content 0.17% in new production, down from 0.5% in 1942 samples. Nickel, trace amounts only. Carbon, dangerously high at 0.68% in some plates. The numbers tell a story of substitution, desperation, and failing chemistry. How widespread? Panthers built after February 1944 show consistent defects. Tigers vary, some good, some catastrophic. Production quality is erratic. Strategic implications cascade. If German armor is brittle, American 75 mm guns become more effective. British 17-pounders can penetrate frontally at longer ranges. Soviet 85 mm guns, previously marginal against heavy German tanks, now crack armor plates open. The tactical calculus shifts. Field manuals update. Aim for welding seams. They fail under stress. Multiple hits on the same area will induce cracking. High explosive shells against side armor can cause catastrophic spalling. But there's a deeper question. Why? British intelligence traces supply chains. Nickel refineries in Norway, bombed. Manganese mines in Nikopol, Ukraine, lost to Soviet advances in February 1944. Molybdenum from Knaben, destroyed twice, production never recovered. Finnish nickel from Petsamo, supply uncertain. Germany is fighting with chemistry it can't obtain. A Soviet technical officer examines a destroyed Panther Ostfagay. The glacis plate shows carbon content of 0.75%, 50% higher than maximum recommended for armor steel. Manganese at 1.2%, 4 times normal. The combination creates steel that's hard enough to pass hardness tests, but lacks the internal structure to absorb shock. It's armor by numbers only. Under impact, the crystalline structure fails catastrophically. The tank becomes its own fragmentation grenade. Production statistics tell the final story. 6,000 Panthers built, hundreds lost to mechanical failure, hundreds more to armor that couldn't protect their crews. The steel shortage isn't limiting German tank production. It's killing German tank crews. July 24, 1944. Normandy bocage, dawn light filtering through trees. The Panther commander peers through his cupola. 300 meters ahead, Sherman tanks are moving through the hedgerow. He estimates 5 targets. His 75mm L-70 can punch through their armor at this range like paper. Gunner, target tank left. The first 76mm round hits their glacis plate. It doesn't penetrate. The American shell ricochets upward with a metallic shriek. Standard deflection, textbook. Then the commander hears it. Crack! Not the impact. This comes half a second later. A sharp crystalline snap like ice breaking. He looks down. A fracture line has appeared in the glacis plate, running from the impact point toward the driver's compartment. The crack is widening. Reverse! Reverse now! The driver throws gears. The Panther lurches backward. Another 76mm round hits their right side armor. 60mm, thick, angled, should stop it easily. The plate doesn't stop anything. It shatters. The projectile punches through brittle steel that offers no resistance. The shell enters the crew compartment at waist height, detonates against the ammunition storage. The gunner has 1 second to understand what's happening before the Panther's own shells cook off. The commander is thrown clear by the explosion. He lands in the mud, ears ringing, watching his tank burn. The side armor where the shell penetrated looks wrong. The edges of the hole are fractured, crystalline. Chunks of armor plate litter the ground around the chassis. That wasn't penetration. That was disintegration. 200 meters away, another Panther takes 3 75mm HE shells against its side. The third shell doesn't penetrate. Doesn't need to. The armor plate develops stress fractures, then simply breaks away in sections. Crewmen bail out screaming, their protection stripped away by metallurgical failure. The commander watches American tankers advance cautiously, expecting heavier resistance. They don't understand yet. The Panthers aren't dangerous anymore. They're coffins wrapped in glass. Watertown Arsenal Metallurgical Laboratory, Massachusetts, August 1944. The sample sits under the electron microscope. 3.25 inches of Panther glacis plate, flame cut from a vehicle captured in France. The microstructure tells a brutal story. Dr. Richardson adjusts the magnification. Normal armor steel shows fibrous fractures, elongated grain structures that absorb energy by deforming plastically. This sample shows something else entirely. Crystalline fracture planes, massive martensite formations, grain boundaries decorated with carbide precipitates. Run the spectroscopy again. The results confirm initial readings. Carbon, 0.68%. Far above the 0.50% maximum for weldable armor steel. At these concentrations, carbon forms iron carbides that segregate along grain boundaries, creating microscopic stress concentrators. Under impact, these boundaries become fracture initiation sites. Manganese, 1.15%, triple the recommended amount. Combined with excessive carbon, this creates a hardening effect that increases brittleness exponentially. Chromium, 2.1%, high but manageable, except without sufficient molybdenum to moderate its grain coarsening tendency. Molybdenum, 0.15%, a trace, useless. The metallurgical failure chain is clear. Molybdenum normally prevents temper embrittlement and maintains fine grain structure during heat treatment. Without it, the high chromium content causes grain coarsening when the armor remains at elevated temperature during cooling. Large grains mean reduced toughness. But the heat treatment evidence is worse. Richardson examines the hardness gradient across the plate thickness. A properly tempered plate shows consistent hardness throughout. This sample shows extreme variation. Surface hardness 280 Brinell, core hardness 240 Brinell, with severe gradients indicating improper quenching. Oil quenching. The evidence is unmistakable. Oil quenching induces rapid surface cooling while the core remains hot, exactly what creates differential thermal stress and residual tension. The plate emerges harder than specification requires, but with internal stresses that make it fracture-prone. Impact resistance? The technician checks his notes. 23 foot-pounds at room temperature. Should be 70 minimum for armor steel. Richardson writes his conclusion. The armor plate examined demonstrates metallurgical characteristics wholly unsuitable for ballistic protection. Brittle failure under impact is inevitable. The Germans have created armor that passes hardness tests, but shatters under fire. Panther Crew Barracks, Western Front, September 1944. Unteroffizier Schmidt sits on his bunk writing a letter he knows sensors will destroy. His hands shake slightly, not from fear of combat, but from knowing his own tank will kill him. The armor cracks like porcelain. We joke that we're riding in a steel coffin, but it's not steel anymore. It's something else, something wrong. Across the room, his driver refuses to sleep. The man saw what happened to Mueller's crew. Their Panther hit by a 75mm HE shell that shouldn't have penetrated. The armor section simply broke away. The explosion that followed was their own ammunition. Morale reports document the psychological collapse. Crews request transfers to older Panzer IVs. Some refuse new Panthers entirely, claiming mechanical excuses. Commanders know the truth. The men don't trust the protection anymore. A loader describes the sound. You hear the hit, normal. Then this crack, like ice on a frozen lake. You know the armor has failed before you see the damage. Allied POW interrogations reveal German tactical adaptations born from metallurgical terror. Panthers stay hull down, minimizing exposure. Commanders position Panzer IVs 1,000 meters behind Panther formations to protect their vulnerable sides. Crews angle tanks obsessively, knowing direct hits will crack the plates. From a captured diary, better to be hit in 1942 steel than protected by 1944 garbage. The old tanks bent, these shatter. I've seen turret armor crack from a glancing blow. How do you fight when your protection is brittle as glass? In Brandenburger Eisenwerk, a German inspector finds another sabotaged cooling bath. The temperature gauge has been manipulated from months. Thousands of armor plates improperly heat-treated. He doesn't report it. What's the point? The molybdenum is gone. The nickel is gone. The manganese is running out. They're welding together coffins and calling them Panthers. Soviet Ni-48 Testing Facility, Moscow, October 1944. 2 captured Panther Ausf G tanks sit in the firing range. Engineers have specific orders. Determine why German armor is failing so catastrophically. The first test fires an 85mm BR-365K round at the glacis from 1,500 meters. Standard anti-tank engagement range. The shell should ricochet. The angle is steep. The armor nominally 80mm thick. The round penetrates. Not through ballistic force, but because the armor cracks on impact. The fracture propagates along crystalline boundaries, and the shell punches through compromised steel that offers minimal resistance. A Soviet metallurgist examines the breach. Crystalline fracture, no ductility. This isn't armor steel, it's high-carbon structural steel poorly heat-treated. They test the second Panther's side armor with 76mm rounds. After 3 hits in the same general area, a section of armor plate simply detaches and falls away. The metallurgist photographs the fractured edges for the technical report. Conclusions? German armor quality varies wildly. Some plates from Tigers show adequate properties, properly tempered, reasonable alloy content. But Panther production from 1944 is consistently defective. High carbon, insufficient molybdenum, improper heat treatment, inconsistent quality control. The intelligence implications spread immediately. Soviet field manuals update. German heavy tank armor can be defeated through cumulative damage. Multiple hits in the same area will induce catastrophic cracking. American ordnance testing at Aberdeen confirms similar findings. British intelligence photographs cracked Panther turrets for training materials. The message is consistent. German armor has failed at the molecular level. But some German vehicles still show excellent protection. Tiger tanks built in early 1943. Panthers from specific factories. The quality is erratic, dependent on which forced laborers sabotaged which production lines, which stockpiles of proper alloys remained, which heat treatment operators maintained correct temperatures. German procurement officers know the truth. They receive field reports of catastrophic armor failures. They order production increased, because brittle armor is better than no armor, and there are no good options left. May 8, 1945. A Panther Ausf G sits abandoned in Berlin. The glacis plate shows 3 distinct crack patterns radiating from impact points, none penetrated. All compromise the armor structurally. The crew abandoned the vehicle not because it was destroyed, but because they could no longer trust the steel around them. An American technical intelligence officer photographs the damage for post-war analysis. The cracks tell the complete story. Brilliant engineering destroyed by resource starvation and desperate chemistry. The final accounting is devastating. By June 1944, molybdenum had vanished from all German armor production. Nickel became trace-only except in the heaviest plates. Manganese supply collapsed when Ukraine fell. Chromium remained, but without modifying elements, it induced grain coarsening and brittleness. German metallurgists had tried everything, increasing carbon to maintain hardness, boosting manganese for strength, adjusting heat treatment cycles. But chemistry is unforgiving. Remove molybdenum and steel loses toughness. Add excessive carbon and weldability collapses. Rush heat treatment and martensite forms. The result? 6,000 Panthers built with armor that could shatter under fire. Thousands of crew members protected by steel that had become ceramic. The legacy extends beyond World War II. Modern armor steel still uses molybdenum, typically 0.25 to 0.40%, for exactly the reasons German engineers discovered in the 1930s. It prevents temper embrittlement, maintains fine-grained structure, and provides impact toughness that carbon and chromium alone cannot deliver. The Panther's armor failure became a metallurgical case study, a cautionary tale about substitution chemistry and the importance of quality control under pressure, about how strategic bombing can target not factories but the periodic table itself, about how the finest engineering in the world fails without the right elements. The Germans designed perfect steel. Then they lost access to the alloys that made it work, and thousands died in tanks that cracked like porcelain. Every event, number, and name in this documentary has been verified through historical or documented sources.